Can you see something? Oh, there it is, right? Okay. Okay guys, now basically what is left here from chapter 4, okay, are the exercises, but the exercise is quite boring, and they are basically are the same as the exercises in the previous chapters, okay, so all you have to do is just calculate mean and variance and all this kind of stuff. So this is something that we don't need. I'm not sure whether or not you've seen this, but the lecture notes have been updated. Okay, so there is also chapter 5. Okay, and next week you're going to get chapter 6. I will try to summarize and the topics that you can choose from, and basically what you could do is you could contact me. Okay, so I will announce this. What I would give you is I give you the corresponding methods that you can take, and I would like to ask you to look up at a certain example from an empirical study. Okay, there is a software. It's called the eViews. Okay, and the eViews is the student version. The student's version is enough. Okay, and it's free. Okay, so you can download the student version, and that will be enough for your paper. Okay, so you don't need to have like more sophisticated methods, whatever. And these are the methods that I put together a list for the methods that you can choose from, and I would like you to look up an example on your own and repeat this. Okay, so just repeating simple empirical papers. Okay, so then of course you would need to quote them, and that would be your seminar paper. Okay, so that's what you're supposed to do. And you find examples in the literature that I gave you. Okay, so in the book from Hustler, that was the primary literature. It's in the library, so you can check it out. And I would like you to look into. I would like to ask you to look into that literature. You find a lot of examples for each method, and of course, and also like a list of complete literature, so you can look that up. And what you could do is for seminar paper is you would repeat the corresponding examination. Okay, so you collect your own data. Okay, so either an updated data. Okay, let's say the paper is from 2010. Okay, so you would just extend this for 2018, right? Or you could do this for another data for a different country, maybe. Okay, so if it's, let's say, the empirical studies from the United States, that you could do this for, like, let's say, German data or French data or whatever. Okay, so that is something that you could do as an option. Okay, but I would like to talk to you. Okay, so I tried to do this by the end of this week, and you will find a list. So I will announce this. And then I would ask you to look into the literature and to collect some papers that maybe you're interested in, and talk to me about this. Okay, so that will be your paper. The paper is just, or has to be like 4 to 5 pages. Okay, so it doesn't have to be long. One study is enough. Okay, maybe you would compare it to another study. That should be fine. Okay, so let's say if you have 4 to 5 pages, let's say 1 to 2 pages of your study on your own, and the other 1 to 2 pages are comparing your study to the previous literature, so what others have found out or figured out, basically. But this is just more or less, a literature review of the paper that you based your study upon. So it's relatively simple. Okay. So and that would be your seminar paper again. So this is relatively easy for the concept, but I will tell you exactly what I would expect from you. Okay, so how would I set up a paper, this and that, whatever. Okay, so what are the things that I consider to be important. Okay, so you will get detailed information about that. And yeah, so this is how it goes. Okay, now today we'll start with chapter 5, and chapter 5 will be a model estimation and testing. Okay, among others, I will repeat the ordinary least square regression. Remember the ordinary least square regression, maybe from regression analysis. I will base the next assignment, it's going to be based on that, because your task, and I can tell you this already, your task will be to implement an ordinary least square estimator for an autoregressive model. Okay, so for an autoregressive model, you have to implement an ordinary least square estimator. Okay, and that will be your next assignment. And you have to send the program to me. So you submit the program, I will test it. Okay, and based on my tests, I will give you your final grade for that. So, but what is important for me as well is that you also do a documentation. Remember what the documentation was when we're looking at the MATLAB kind of thing? Okay, so you have to document your function. Okay, so for me it has to be clear. Of course, I mean, if I read your code, I understand what you're doing in most cases, but sometimes I don't. So what is important for me is that you provide a documentation, which is, I would say, almost as important as the code itself. Okay, so that would be basically your task. Again, an ordinary least square estimator. Okay, so this will be the second assignment. I will announce this. Okay, so but let me just, okay. So the second assignment will be the ordinary least square estimation. Okay, so ORLS estimation of the autoregressive model. Okay, so an autoregressive model. Okay, autoregressive model. Okay. All right. Maybe the first order. We're starting with the first order first, and then we extend this. Okay. So that would be the first order autoregressive model. Okay. So basically, yt equals the constant plus a times yt minus 1 plus the noise. Okay, and what you have to do is, or you will have to do is, you have to implement an ordinary least square estimator, okay, on your own. All right, so given a time series, so what I would do is, like, you have an input argument, it's a time series, a sample, let's say, and you implement an ordinary least square estimator, and you also, okay, so you need to have the estimators, okay, so the estimators here for that, and the test statistics too. Okay, I will announce this so you will see it. Okay, is that clear from this point of view? So this is what I do today, so I repeat this, and tomorrow maybe also, and so later you can submit it. Okay, so I will need a program especially, okay, so the estimators and the test statistics. Okay, so we look up the formulas in a general case, and then you would apply this here for the second assignment. Okay, so this will be it, and I will announce this either tomorrow or today. I think it should be also today. Okay, now, okay, so chapter number 5 will be just about that. So basically, this is the model estimation and testing. Sorry. Okay. All right. So among others, as I announced, you're going to need the ordinary least square estimator. Okay? Now, basically what you would do is, okay, so you have a certain type of stochastic process. Okay, so Y is a stochastic process. Okay? And what you have is, let's say you have an estimator. Okay, so Y, this is called Y hat. Okay? So this is an estimator at time t, so you estimate something at time capital T for point h, okay, or for time t plus h. Okay, so this is the estimator, okay, or the estimation or forecast. Okay, that's called forecast. Okay, for the stochastic process Y at time t, okay, which is either today or sometime in the future. Okay, so it can be something either today or in the future, for time t plus h. Okay, so this is the notation that I use. Okay, so what I mean by that is this. Okay, so h is, of course, right, so where basically h is greater than 0. Okay, so we look into the future. So what I mean by that is this. Okay, so let's suppose that here you have the time. maybe this is the current time without loss of generality, right? So here you have the time t, and let's say here you have the time t plus h, and at that time, okay, you would forecast the process here for t plus h. Okay, so at time capital T, you would make a forecast for the process for time t plus h, which is not known. Okay, all right. So that's what you would do, and that's why I call this an estimator or the forecast. Now, how would you do this? Okay, so how would you basically what you would do? I mean, the best estimator, maybe you've known and you've learned this in statistics. I mean, I'm supposed to lecture you, so obviously you have. All right, let's be honest. Is that the mean of the process? I mean, suppose that the process is stationary, and the basic approach here. Okay, so this is the basic approach here for the estimation. Okay, is that you consider the estimator or the forecast of the process at time t for time t plus h to be equal to the conditional expectation of the process. Okay, so you take basically so I take this here. So the conditional expectation of the process, okay, at time t plus h, given its past, and the past, okay, I mean considered to be from at point t, or capital T. Okay, so this is the past here. So y t, okay, then you have y t minus 1, okay, blah blah blah, y t minus 2, etc. So this is the past, okay, of the process. All right. So what I'm talking about is this. Okay, so this is the past. Here you have it, right? Either it's bounded from below or not. But okay, so this is the past given the process, and this is the conditional expectation. This is the basic approach for estimation. Okay, so that's how you would forecast the process. I mean, let's say if I would, ask you to implement, let's say, certain forecast model. Okay, so forecast model, and then this is how you would do it. Okay, so that would be also, let's say, maybe, okay, so you have the estimators, you have the statistics, and then you forecast something like, whatever. Okay, basic approach. Anyways, okay, now this is how it works, and of course this is okay, so the forecast is set to be optimal. Okay, so this is basically definition. Okay, so all right, so this is the forecast. Okay, so the forecast, and I say this as a notation is y hat at point t for time t plus h is set to be optimal. Okay. Okay. So when is it optimal? It is optimal if it minimizes the so-called mean squared prediction error. Okay. So if it minimizes the so-called mean squared prediction error. Okay. And I'm going to find this as follows. Okay. So basically, the mean squared prediction error is equal to, okay, so I'm using the letters mean squared prediction error. Okay. So MSP, right, is the mean squared prediction error of the forecast. Okay, so the mean squared prediction error of the forecast at time t for time t plus h, okay, is as follows. Okay, so basically this is, okay, so this is the expectation. Okay, so this is the expectation operator of the following squared sum. So here you have basically the estimator. Okay, so this is the estimated or the forecast, you say, and then you have minus and basically the observation that you would have. Okay, all right, so you take the difference of your forecast minus basically your your observation at that time, for which basically the forecast is constructed. You take the square of it, and then you take the expectation of it. All right? Okay. So basically, I mean, this is called optimal. Okay. So if that is minimized, okay, so this is the mean squared prediction error. So on the average, I mean, you cannot expect that your forecast will be always correct. This is something that you can't do, right? It's impossible, almost surely, let's say. Okay, if you're familiar with the term almost surely. So almost surely you're gonna fail. Okay, so your forecast will not hit the true value. Okay, but on the average it should. Now, of course, there are some errors regarding this. Okay, so basically sometimes you estimate it to be too high, or sometimes you estimate it to be too low. It doesn't matter. So, but on average, okay, the variance basically, or to be precise, when you just said the mean squared prediction error should be minimized. Okay, and if it's minimized, then the forecast is called optimal. Okay, now basically, I mean, this maybe you're familiar with the. I mean, I will continue here, so I will explain this what you will have here. But maybe you're familiar with the following concepts. So the variance of a random variable is or was equal to the expectation of the square minus the square of the expectation, right? Remember that? So if I use that, just rearranging that, because this is something that you would have here, that the expectation of the square is equal to the variance of the random variable plus the square of the expectation. Okay? So I'm taking that and I'm using this here for that formula. So this is going to be equal to the variance, okay, of the prediction error, let's say. This is the prediction error, right? So the variance of the prediction error, okay, plus the expectation, or the square of the expectation of the prediction error, right? So the expectation of the square of the prediction error. Okay, so this is the expectation of the prediction error. Okay, I need a little more space, as I see it right there. So this is the expectation, okay, of the prediction error, okay, and you take the square of that. So the variance of the prediction error plus the expectation of the square of prediction error is going to be equal to the mean squared prediction error. This is the prediction error, right? Okay, so what you have here is the prediction error. Okay. So the mean squared prediction error is not just the variance of the prediction error, okay? It's the variance of the prediction error plus the square of the expectation of the prediction error. Now, of course, you would expect that the expectation of the prediction error is 0 in most cases. Okay, so if the expectation error, okay, so if the, let's say, if the expectation is equal to basically to this expression, or the prediction error, or the expectation of the prediction error is 0, then the forecast or the estimator is unbiased. Bless you. Okay. You're welcome. Okay? You understand this? Okay? Now, okay, so I will generate basically the following lemma. Okay, so if we set this equal to, I mean, this is going to be the basic approach here. So if you take that, okay, as basically your forecast, then you could have the following properties. So basically you would have an, let's say we have an ARMA process, okay, so this is called lemma. And you could use this for an ARMA process, okay? So basically you would have that Y is a ARMA process, okay? So this is the autoregressive moving average process. You've probably seen this before, okay? So this is what we had last week, okay? So we have the autoregressive part and the moving average part, okay? So basically this is split it up, and okay, this is of order P and Q. It doesn't matter, so the order is not important here. Okay, it could be from order P and Q, but it's not important. Okay, so I don't need P and Q here in my case. And basically let the forecast denote as follows. So this will be the forecast. So I use the forecast at time t for time t plus h as follows. So basically I would use the conditional expectation, as I said before. Okay, so the conditional expectation of the process at time t plus h given its past, okay, namely at time t, or capital T, right? So you have yt, and then you have yt minus 1, yt minus 2, etc., etc. So this is the past of the process, okay? And suppose I'm using that for forecasting values for the stochastic process at time t for time t plus h, etc. Okay, I suppose that this be the case. And then we have the following, okay? And what also important is that the process is supposed to be stationary. So, and let y be stationary, okay? So if the process is stationary, then we have the following properties of the prediction error, or the basically of this forecast. So the first property is that the prediction error is unbiased, and I was just basically mentioning what unbiased means. That the expectation of the prediction error is 0. Okay, so the expectation. Okay, so the expectation of the prediction error is 0. So what does it mean? Okay, so basically this is called unbiasedness. Okay, so then you would say that the prediction or the forecast is unbiased. Now what does it mean? Okay, it basically means that the expectation here, okay, the expectation of the forecast error, okay, namely this is the forecast for time t plus h, and this is the observation at time t plus h. Okay, now of course you don't have the observation t plus h. You don't have it now, right? But you could take the expectation of the difference, and this is the prediction error. So the expectation of the prediction error is supposed to be 0. So in that case, if the process is stationary, and assuming that I'm using this as as a forecast, so this approach, namely the conditional expectation of the process, given its past, then I would find that the expectation here is based, or the expectation of the forecast error is 0, which is relatively easy to show. Okay, using the law of iterated expectations, you already have this. Okay, so using the law based on the law of iterated expectations, basically you would have that the conditional expectation is equal to the expectation of the process, because the expectation does not depend on time t. Okay, so only basically in time lag. Anyway, okay, so this is relatively easy to show. On that case, so this is called unbiasedness. Okay, so the prediction error, or the expectation of the prediction error is 0, so meaning that the forecast is unbiased. Okay, basically, as I said before, it doesn't mean that you're always going to hit if you forecast values for the process. It doesn't mean that necessarily that you're always going to hit the true value. Basically, it's never going to be the case, but on the average you do. This is what it means. Okay, so the expectation of the error will be 0. So on the average you will. Okay, now the second part of the property here of this forecast error is that it converges in probability. Okay, so you have convergence in probability. Okay, so basically this means that following. Okay, so maybe you're familiar with this concept. So this means that the forecast, okay, converges, let's say, to the expectation, okay, of the process, and this is the process is stationary, so basically it doesn't matter what kind of expectation you have, because the expectation does not depend on t. Okay, so that could be also basically capital T plus h, so I'm rather using that notation. Okay, again, because it doesn't matter, because the expectation does not depend on t. Okay, so but that makes more sense here from this point of view. Okay, so basically this does not mean that this is going to be always the same, but this means that it converges in probability to that value. Now, as a consequence, this means, okay, so since the forecast error is 0, this means that basically that the variance of the prediction error will converges to 0. This is going to be basically the consequence. Okay, so this is basically, I mean, the convergence in probability, that the forecast is converges in probability to expectation. Okay, as basically h converges to infinity. Okay, so you're going to get the expectation of the process in the long run. Okay, and this is what the process converges to. So as a consequence, you have that the variance of the prediction error converges to 0, because otherwise it wouldn't work. Okay, so the variance of the prediction error will converge to 0. Converge to 0. Sorry. Okay, and the third property is that the forecast is optimal. Okay, so we have the optimality. So this forecast, okay, is optimal, meaning that the mean squared prediction error is minimized. I mean, this is quite easy, right, to see, because, okay, optimality means that the mean squared prediction error is minimized. Okay, so if, let's say, the forecast converges in probability to the expectation of the process, then basically you would have that the variance of the prediction error converges to 0. Now, if the variance of the prediction error converges to 0, then basically you would have that the mean squared prediction error is minimized. Okay, in optimal case. All right, but this is something that you don't need to consider. Okay. Now, okay, so now we're not gonna show this. But again, I mean, here, in order to demonstrate this, so here in this expression, you would have the variance of the conditional expectation, right? So the variance of the conditional expectation, right, plus the conditional expectation of the variance is based on the first assignment, right? The law of total variance, okay, will be the variance of the process. Okay, but now I'm gonna skip this, so you can do this as an assignment if you like. Okay, now let's see how do we basically how in most cases how this forecast will look like. So let's say if we have an autoregressive process of order 1. Okay, so let's say the first order autoregressive process, then basically we'll have, okay, so I mean, how does it look like again? So yt equals a constant plus a times yt minus 1 plus the noise. Okay, so this is the first order autoregressive process. Then basically the forecast, okay, so the forecast here of, or at time t, capital T for time t plus h, is going to be as follows. Okay, so here you have v times 1 minus h to the power of h divided by 1 minus a, okay, and then plus a to the power of h times y capital T. Okay, so this is going to be the forecast. Again, so this is capital Y, capital T is known. So assume that is known, and the past as well. Okay, so you only need to, basically you need the last observation. Okay, so you can see this here. This is the last observation of the process. Okay, okay, so you don't need any other observations. Only the last one that you have, and you use that to forecast the others. Okay, now as basically as h converges to infinity, this expression here, the last one, will converge to 0 because this process is stationary, right? So the process is stationary. So if, I mean, remember this, okay? So the process is stationary here for if and only if the absolute value here of that expression is less than 1. Now, if the absolute value here of the constant is less than 1, then basically this expression will converge to 0 as h converges to infinity. Okay, so then basically the forecast will be and just v times 1 over 1 minus a, which was the expectation of the process. Okay, remember that. Okay, so I hope that you remember this. Okay, now let's see why this is. Okay, so basically, I mean, this is something that we should consider. Okay, so I want to show you why this is. Okay, and this is part of also of the exercises, but it's actually here, so I want to show that to you here. And this is what we're gonna look at. Okay, so this is the forecast, and then we're also going to compute the mean squared prediction error here of that, so you're going to see how it works. Okay, is that clear? Now, okay, so why is that? I'm going to continue, and the answer is relatively simple. So if you have an autoregressive process of order 1, so that means that yt at point capital T is going to be equal to the constant plus the parameter, okay, times y capital T minus 1 plus the noise. Okay, maybe basically at point T. And the same thing applies, okay, if you, let's say, if you change for T plus h, so here you have, so T and then plus h, right? Okay, it's going to be equal to the constant plus the slope times yt plus h, okay, minus 1, obviously, okay, and plus the noise, okay, at point T plus h minus 1, obviously, okay. So if that is true, then this is also true, okay. Now, what would you basically you would get if you, no, sorry, the noise, yes, I would just see it, okay. So I mean, this is, okay, so this is equal to that one, so the noise at point T plus h, of course, okay, so the index would be equal, okay. Now, what would be the conditional expectation? Okay, so what would be the conditional expectation? So I'm using that, okay, so basically to the forecast, because the forecast will be the conditional expectation, right? So this is going to be the conditional expectation of the process given its past, okay? So the conditional expectation of the process given the observations yt minus 1, etc., etc. So given the past of the process, this is going to be it. Okay? Now, obviously, if you have that, okay, so you can introduce here that operator on this expression. Okay, so you introduce here the conditional expectation operator on this side here. Okay, so the conditional expectation here of this side, okay, will be equal to the conditional expectation here of that one. Okay, so this is what you would have. This is going to be the conditional expectation of the total thing. Okay, so I'm talking about this one. Okay, so this one you have it here. Okay, so therefore I'm just going to replace it by it. Okay, so this is what you have. So this is the conditional expectation of the constant plus a times blah blah blah. So you have y t plus h minus 1 and plus the noise. Okay, conditioning on the past of the process. So here you have yt, here you have yt minus 1, and so forth. Okay, so what I'm doing is just replacing that expression with that. Okay, what basically the expression is. Okay, now this is relatively easy to examine, because what you have here is that this is going to be the constant plus a times the expectation, right? So the linear transformation, or the expectation of a linear transformation, is going to be equal to the linear transformation of the expectation. So here you have, this is going to be the constant plus a times the conditional expectation, okay, of yt plus h minus 1 given the past of the process. Okay? Okay? So given the past plus the expectation or the conditional expectation of the noise, right? Now guys, the conditional expectation of the white noise is going to be always equal to 0. So I will leave this, okay? So then plus 0, you can You could add this here, but you don't have to, right? Okay? So now, basically, I mean, using complete induction, okay? So what you have here is, and let me just summarize this, because that's basically what you have, is that the forecast, okay, at time t for time t plus h is equal to the constant plus a times, and this is what? This is the forecast, okay? And then for what? This is the forecast at time t for time t plus h minus 1. Okay? So this will be the forecast at time t, all right, for time t plus h minus 1. Okay, so here you have h minus 1 and so forth. Okay? You understand this? Okay? So that's what we have figured out here in this case. Okay? So the forecast at time t for time t plus h is going to be equal to the linear transformation of the previous forecast. Okay? For the previous point of time that you had. Okay? Now you could go back basically. So okay, so here you have h, and so then here you have h minus 1. So if you replace that, okay, so I mean you could substitute here for it. Okay, so basically I mean you could use that formula to calculate the forecast for time h minus 1, right? So that is something that you would use here for induction. So this will be the linear transformation of the forecast at time t, all right, for time t plus h minus 2. Okay, so here you substitute basically h by h minus 1, right? Okay, so then you would have h minus 2 here. You understand? So then you would get analogously, okay, so what I'm doing here is I'm substituting this expression here by that one. Okay, so here I'm going to put that here into it. Okay, so basically, I mean, this is what we did for the autoregressive process as well. So finally, you would get the forecast at time t for time t plus h is going to be equal to, and this is what you would have. So this is going to be v plus 1 plus a, okay, plus a squared times the forecast, okay, at time t for time t plus h minus 2. Okay, so finally, I mean, this is what you would get if you would put that here into it. Okay, so you have a times v, and then you have a times the forecast for at time t for time t plus h minus 2, which will result in v times 1 plus a squared times the forecast at time t for time t plus h minus 2. Okay, and so forth. Okay, so, and then you could also do this, I mean, you could also like generalize that for another expression. So you mean if you go back even further in time, so you would have v times 1 plus a squared, right? Okay, so then plus a to the power of 3 times the forecast here. Okay, so the forecast, sorry, I always forget these heads, at time t for time t plus h minus 3, so we even go further in the past. Okay, so by using induction you would get that. Okay, so here you could substitute for the forecast for time t plus h minus 2, okay, by using that formula here. So the forecast for time t plus h minus 2 will be equal to the constant plus the slope times the forecast for time t plus h minus 3, right? Okay, so this is how you would get this result. Okay, now you could do this for like whatever. Okay, so we do this h times. Okay, so then, okay, so finally, okay, so then you do this for 4, 5, 6, 7, 8, 9, 10, whatever. Okay, so the final one will be h. Okay, so this will be the final one. Okay, you understand this what I'm doing here. So this is complete induction. Okay, so then you have 2, 3, 4, 5, 6, 7, blah, blah, blah. Okay, so then basically you recognize a pattern. So the final one will be h. Okay, so here you have it. Okay, so this is going to be the constant. times 1 plus a squared plus blah blah blah. Okay, so then you have a cubed, a to the power 4, a to the power 5, blah blah blah. So then I'm going to stop at point a to the power of h minus 1, so that will be the final one. Okay, so then you have times a to the power of h, right, times, and then you have the forecast at time t for time t plus h minus h. Okay, so you have t plus h minus h, which is, of course, h minus h is going to be equal to 0. So this will be the forecast at time t for time t. Now the past, of course, is given, okay? So yt is, of course, given because this is something that you observe right now. So the forecast of that would be equal to the observation. Okay, why would you do something else, right? Okay, this is a nonsense. Okay, so basically this is equal to the observation yt, obviously, right? That's obvious. Okay? Okay? So, and then you could simplify this formula. Okay, so what I'm doing here, and this is going to be the formula for the geometric series, guys. So see, you have, okay, so here you have the formula for the geometric series. So let's say the sum starting at j is equal to 0 till h minus 1. Okay, and then you have a to the power of j, and then that expression, which is a to the power of h times yt. Okay, so this is just simplifying it. Okay, now I'm applying the formula for geometric series, of course, and applying the formula for geometric series, you would get that this is going to be equal to 1 minus a to the power of h divided by 1 minus a, obviously, and then you have the rest. Okay, so this is how it works. Okay, that's a statement that I was summarizing in the previous section. Okay, right? Okay, so that's not difficult. Now, of course, we calculate the mean squared prediction error here. So the mean squared prediction error of this forecast. Okay, so the mean squared prediction error of the forecast at time t for time t plus h is going to be equal to, I mean, this is the expectation of the square of the prediction error, and the expectation of the square of prediction error, we had this, is going to be the variance of the prediction error plus the expectation, or the square of the expectation of the prediction error. Okay, so here we have the variance of the prediction error. Okay, so the variance of the prediction error. Okay, and then, all right, so then plus the, basically, the expectation. Okay, so the expectation of the prediction error, right? Okay, so here you have it. Okay, the prediction error, right? So you have yt plus h. Okay. Now, of course, and this is something that we can basically simplify.
Does it have to be squared?
Yes, yes. Okay. Okay. So as soon as this is given, it's going to be equal to 0. Okay. So basically, I mean, if we assume that, I mean, probably that this is going to be it. So this is going to be the mean square prediction error. And what you would figure out here is that this is, I will skip this. So this is something that it's quite boring, so I'm going to skip that. But you would find that this is going to be equal to a to the power of 2 times h times sigma squared times 1 over 1 minus a squared, which is an expression that relates to the variance here of that. Okay, so I'm not going to elaborate on that because this is something that you don't need to consider. Okay, now as you can see this here, that the mean squared prediction error, okay, so this is going to be the mean squared prediction error, or let's say the variance here also of the process, and this is going to converge to 0 as h converges to 0. Meaning that basically, I mean, this is, okay, so the absolute value here, okay, so since the absolute value here is less than 1, we have that, we have that the mean squared prediction error, okay, so the limit of the mean squared prediction error, okay, of the forecast, okay, will converge to 0, okay. Right. So that's what you're gonna get, okay. Which meaning that basically the forecast converges in probability to the expectation as a consequence, okay. Now, guys, okay, so I don't want to bore you with that, but this is just something that we have. Now, how would you generalize this for, okay, so this was this case for the first order autoregressive process. Now, how would you generalize that for the higher order processes? Okay, so this is going to be, I'm going to just give you the results, so based on that. And this is, okay, so let's say if y is an autoregressive process of order p, then you would get the following results. So then basically the forecast, okay, at time t for time t plus h is going to be equal to, okay, so you have a higher order autoregressive process, and that is quite simple. So you're going to have the constant plus a1 times the conditional expectation, okay, of the process at time t plus h minus 1 given its past, okay. Okay, so given the past of the process, this is going to be it. And then you have a2 times the expectation, okay. Okay, so at time h minus 2, of course, okay, given the past of the process, so yt, and then you have yt minus 1, and so forth, okay, and blah blah blah. So then the last thing will be equal to ap, right? So ap times the expectation, okay. So here you have the expectation of the process at time yt plus h minus p, given the past of the process at time t. Okay. Now here in this expression, you can clearly see something. Okay. So because, I mean, look. Okay. So we go back here in time. So here you have t plus h minus 1. Okay. And here you have t plus h minus 2, and so forth, right? And here you have t plus h minus p. Okay. Now it could be the case that p is larger than h. Okay, so if p is larger than h, basically, then here you have t minus something, right? So for instance, t minus 1 or something. Now the expectation of t minus 1 given yt is of course already observed. So that would be already the observation, you understand? Okay, so let's say if the index here, okay, so this, I'm talking about this index, okay, or these indices, okay. So if any of the index is less than basically, I mean, less than t, okay. So let's say, for instance, I mean, okay, so what I would do is, okay, so what is the expectation here? And this is what I would consider. Okay, so what is the expectation, or the conditional expectation? So I'm going to focusing on the expectation here, so t plus h, and then I will generalize this, let's say, minus j, okay? So j could be anything from 1 to p, okay? So these are the values that it can take, okay? So either 1, 2, or p, okay? And let's say if you find that basically, let's say t plus h minus j is less than t, or less than or equal to t, then basically you would have the observation itself. Okay, and this is basically you would, okay, so in this case, let me just just demonstrate this. Okay, so in case, let's say that h minus j, okay, so h minus j is less than or equal to 0. Now if h, as again, so if h minus, okay, so let's say for instance this one, so if h minus p, let's say, is 0, okay, so if h is equal to p, here in this expression, then you have yt here. And the conditional expectation of yt, given yt is of course yt itself. So that would be the observation itself, you understand? Okay? Or let's say if it's h minus p is 0 or less than 0, so if let's say if h minus p is equal to -1, now if h minus p is equal to -1, then you're going to also have a past observation, okay? So the expectation of the past of the process, given its past, is going to be equal to the past observation. So that will equal the corresponding observation that you have. Okay, so if let's say the time lag is too large, okay, so already past, you go back in time, but basically the time lag is too large, so then you will get the corresponding observation. So this will be, okay, so this will be the observation at time t plus h minus j. So this will be the observation itself if the time lag is basically too large. You understand? Okay. So I mean, in this example, if we consider, let's say, h minus p here is 0. So if h minus p is equal to 0 or less, then you already have the past of the process. And you don't need to forecast that anymore, because if you already observed it, so you don't need to forecast it. And if it's not less than 0 or equal to 0, okay, or let's say it's greater than 0, okay, basically so what I would have is that if basically that h minus j is greater than 0, then you still have a future value of the process, okay? And you would use the future value just for forecast, so this is what you would have. So this is going to be yt, okay, so that would be the forecast at point t for time h, okay, so h minus j. So then you would use the forecast, okay, which is, or supposed to be, the conditional expectation itself, okay? So that's how you would use the formula recursively. Sorry guys, I forgot, this is not the expectation, this is the conditional expectation, of course. Okay, so I want to explain these expressions here. So I apologize here for that. I wasn't aware of this. Okay, so this is the conditional expectation. Okay, so conditioning on, okay, so here you have it, conditioning on the past of the process. Okay, I tried to add this here to it. Okay, so the expectation, I'm talking about these expressions here.